Our next speaker is Yuma Sugahara. Would you like to share your screen, Yuma? So Yuma is going to tell us about fast outflows identified in early star-forming galaxies at redshifts 5 to 6. Thank you.
Sorry. Thank you for the introduction. I am Yuma Sugahara, a postdoc at the National Astronomical Observatory of Japan and Waseda University. I'd like to present our results in the our last year paper for the first measurements of the galactic outflows in star-forming galaxies at redshift 5 to 6. This is collaborational work with these researchers. So the galaxies are thought to be evolving in a baryon cycling. And this picture is supported by many numerical simulations, but it's difficult to observe this baryon cycle directly, especially for at high redshift. So we are focusing on the outflows in high redshift star-forming galaxies. So in our previous work, we showed that the outflow velocity increases from redshift 0 to 2. So then how about the higher redshifts? So John et al. Suggests that decrease, and Du et al. Shows a flat evolution, so which is correct. And there is no data point at redshift higher than 4. So if we plot a data point at this redshift range, we can see, we can know the average evolutionary trend of the outflow velocity. But there are some challenges for outflow study at high redshift. First, usually to measure outflow velocity, usually we use the blue shift of the absorption lines. So we need a deep rest UV spectra of the high redshift galaxies. It's expensive observation. And moreover, to measure blue shift of absorption lines, we have to know the precise systemic redshift. But unfortunately, there are no strong nebular emission lines in the rest UV spectral range. There is a strong Lime alpha emission, but the velocity or redshift is uncertain for Lime alpha emission. The solution we'd like to present here is the combination of the deep UV spectrum and the recent ALMA observation of the carbon-2 158 micrometer. And the galaxy sample with these two key observations are already open. So we use the archival 7 Lima break galaxy spectra taken by Peter Keck et al. So these galaxies from HZ1 to HZ10 are observed by the Keck of DEIMOS, and we can use the deep rest UV spectrum as well as absorption lines. And these galaxies are also observed by ALMA and detected in carbon-2 emission lines. So we use these carbon-2 emission lines for systemic redshift and to measure out blue shift absorption lines. But unfortunately, the individual rest UV spectra have low signal-to-noise ratio even in this sample. So we stack these deep rest UV spectra and obtain the composite rest UV spectra. So top panel shows the rest UV composite spectrum. We can see the clear Lime alpha emission and the clear metal absorption lines. And the bottom panel is zooming after these metal absorption lines. We can see the absorption lines are blue shifted with respect to the vertical lash line, which is a systemic redshift. And to measure the outflow velocity, we fit the Gaussian-like profile to the absorption lines. Then we define the outflow velocity as a 90% flux of the bottom of the absorption line, and this velocity from the systemic redshift is defined as a true maximum velocity. Okay, let's go to the results. Okay, this figure shows the outflow maximum velocity as a function of star formation rate. These blue, cyan, green data points are taken from our previous study. And this study at redshift 5 to 6, it comes here. The orange data points show the measurements for silicon-2, carbon-2, and silicon-4. And these three measurements are consistent with each other. And please look at the red square. This is a measurement for simultaneous fitting for the silicon-2 to silicon-2 and carbon-2. And this measurement, so the outflow velocity at redshift 5 to 6 is 700 kilometers per second. So this value is much higher than redshift 0, but comparable to redshift 2. And this is our first result. The next, I plotted outflow velocity as a function of the halo circular velocity. We calculate halo circular velocity from the stellar mass with using these relations. Our observational data points are like on a line on a single relation. Okay. And interestingly, our observations are in good agreement with the prediction by numerical simulations. So this black solid line is a 5-year simulations, and the dashed line is illustrates TNG50 simulations results. So supported by these numerical simulations, our observation suggests that the halo circular velocity strongly correlates with the outflow maximum velocity. And this is a redshift evolution of outflow maximum velocity. Our data is consistent with the numerical simulation lines and the previous observational results, Jones et al., except for these data points. So this figure shows the outflow maximum velocity monotonically increases with increasing redshift. And this evolutionary trend is naturally interpreted if outflow maximum velocity linearly correlates with halo circular velocity. Because halo circular velocity is proportional to redshift to the 0.5 at fixed halo mass. So if outflow maximum velocity linearly correlates with halo circular velocity, outflow maximum velocity should follow the same relation. That is, the outflow maximum velocity rapidly increases at lower redshift and relatively flat evolution at higher redshift. I show the outflow maximum velocity is tightly correlated with halo circular velocity. But at the same time, the outflow maximum velocity also correlate with the star formation rate. Then, what galaxy parameter determines outflow maximum velocity, especially throughout all redshifts? To know that, I plotted outflow maximum velocity as a function of the galaxy properties. These figures show as a function of halo circular velocity and star formation rate. And this blue solid line is the best fit relation at redshift 0. And this black dashed line is the best fit relation at throughout redshift 0 to 6. And in these figures, these two relations have similar slopes. This means that the outflow maximum velocity predicted by the best fit relation at redshift 0 can predict the measurements at other redshifts. On the other hand, this is a plot as a function of the specific star formation rate surface density and specific star formation rate. In these figures, these two relations have totally different slopes. This means that star formation rate surface density and the specific star formation rate can explain the outflow velocity at a fixed redshift, but it's difficult to explain with this relation at redshift 0 cannot explain the measurement at other redshifts. Okay, in summary, if there is a fundamental galaxy property to determine outflow velocities throughout all redshifts, it would be the halo circular velocity or star formation rate. Okay, finally, I'd like to compare our result to the recent observations. For example, Alpine survey, in Alpine survey, Gindolfi et al. Shows that the Taiwan 2 emission line have a broad component in highly star-forming galaxies. This broad component would be created by the galactic outflows, and its FWHM is very consistent with our results, our maximum outflow velocity. And Fujimoto et al., who will give talks tomorrow, finds that the spatially extended carbon-2 emissions comparing to the UV stellar luminosity, UV stellar light. So this spatially extended carbon-2 emission might be explained by the past outflow activity. Like these observations, I think the outflow study at high redshift will get much progress with upcoming of new observations. Okay, this is a summary. And thank you for your time.
Thank you very much, Yuma. So we have a couple of questions. Matt Hayes asks, I think I saw various different absorption lines mentioned, C2 and silicon-4. Are the Vmax constant with the ionization potential of the species, or is there some variation?
Thank you. It's a bit difficult question because our results show it's constant. So the carbon-2, silicon-2, and silicon-4 shows velocity, comparable velocity, and comparable velocity with each other. But they have a relatively large errors. So yes, in our analysis with the stacking UV spectrum, these different absorption lines show similar ultra maximum velocities. Yes, that's it.
Thank you. Another question from Roderick Gavertier. Vmax probably correlates strongly with star formation rate, surface density. Could you comment on that?
Yes, thank you. So as the previous papers, outflow maximum velocity will correlate with the star formation rate surface density. But in our paper, I'd like to say the outflow maximum velocity is correlate with star formation rate surface density at a fixed star formation, at a fixed redshift. But with increasing redshift, star formation rate and galaxy size will increase. Will evolve. So at higher redshift, star formation rate will get higher and size will get smaller. So we'd like to check our results show the outflow specific star formation rate surface density can explain the outflow maximum velocity at a fixed redshift, but this relation cannot explain throughout all redshifts. But this should be checked. So this relation will hold at a fixed redshift or throughout all redshifts.
Okay, thank you. There's another question from Daryl Santos. Based on your results, can we consider the possibility that outflows promote star formation activity at higher redshift?
Sorry, outflow should?
So can you consider the possibility that the outflows are promoting star formation activity at higher redshift? Or enhancing?
Yes, it's difficult to show. I think it's difficult to show from our results, because we only see the outflow velocity to see the effect of the outflows to the feedback to star formation rate is we have to measure the outflow velocity and probably outflow mass or energy or something. So to see the effect, like positive feedback, we should see some more, for example, the local galaxies to get more much high SN observations, I think.
Okay, I'll try and squeeze in one more question. So this is from Gareth Jones, a couple of the CAPAC sources show evidence for ongoing merging. Have you seen a difference in the stack when using a subsample?
Thank you. Merging. So I tried to stack the subsamples with, for example, the only HZ1 and HZ10. And we didn't see any difference for the outflow velocities with dividing subsamples.
Okay, I will squeeze in one more. From Ken Zato, are the outflows isotropic? And is there any evidence for collimated features like jets?
Thank you. It's important feature. So the okay, it's important, but it's difficult to determine the inclination or the shapes of the galaxies at a high redshift. So at a lower redshift, like the redshift 0 to 0.5, we can see the inclination effect. But this redshift, it's difficult. So now I'm assuming the isotropic outflows, but it might be affects at this redshift, even at the redshift 6. But in this time, if inclinations affect at high redshift, at redshift 5 to 6, outflow maximum velocity will get increased.